Okay, so people have made the first step right. They've eliminated a variable and they're on track to solving that variable and completing the problem. And I'm fairly confident that everybody can do that. But I want to do something a little different now. So the problem is solve this system by using elimination. Now I've gone ahead and written the system here. There are two ways to eliminate a variable that are fairly obvious. I could multiply the first equation by -3 and the second by 2, or the first by 3 and the second by -2. Now, that would match up the y's, and then I'd be able to solve for z, okay? Or I could make use of the fact I've already got a negative here, so why mess with multiplying by a negative? Let's just multiply this one by 3 and this one by 2. That'll match up to z's, so we can solve for y, okay? So question of which one we want to do. What I'm going to do, because of what I'm going to do here in this blank space that I've left, will work better if we go ahead and bite the bullet and do the negative signs over here. Okay, so I'm going to do -3 times 1 and 2 times equation 2. -3 times the 2 is going to match up with the 2 times the 3. And we're going to end up with this. Now, I've urged you to put these things in columns, okay? And keep your equal signs and your x's and y's and your z's all lined up, all right? There's a reason for that, and it's not absolutely necessary. If you've done all the steps correctly, then you're going to understand, and everybody seems to be doing the steps correctly, okay? So if we multiply this equation by -3, we get -6y plus 12z equals 6. Check me on this. If we multiply this equation by 2, we get 6y plus 12z equals 42. And if we add equation 1 to equation 2, we get 24z equals 48. So z equals 2. Now there's an intermediate step there, and I think everybody's pretty much writing down their intermediate steps, which I think is a very good reason, a very good idea at this point, okay? Because it doesn't take long. And again, it keeps reinforcing something that people still tend to miss sometimes. Although, as a class, everybody is doing pretty well, or to quite well with linear equations. So I'm not too concerned about your ability to solve that. Not concerned at all, actually. Okay. Okay. Well, that's fine. Now, there's a more compact way I can write this. And it should be obvious. And what have I done here? I'm not writing my y's or my z's. I'm not writing my variables, but I am writing the numbers that really determine what the solution is, okay? And if we understand that this is the column for y and this is the column for z, so this really means 2y minus 4z, right? And this really means this is the y column, 3y, this is z column, this means plus 6z. This completely represents the left-hand side, right? And then the right-hand side, I've got these dotted lines here to indicate this is the other side of the equal sign, and clearly that's -2, 21, okay? So again, I've got, instead of equation 1, I've got rows 1 and 2. Okay. So now, if I've got this and I haven't seen this, haven't done this, if I've just got this matrix, because this is called a matrix with the square brackets and everything, and you see that about that in the assignment. You call this the augmented matrix, okay? This part of the matrix has the coefficients of x, of y and z, and we augment it with the right-hand side. That's why it's called an augmented matrix. I'm going to do exactly the same thing to the rows that I did to the equations. So I'm going to do -3 times row 1 and 2 times row 2. I just go through and multiply all these numbers by -3 and multiply all these numbers by 2. Okay? In other words, row 1 all gets multiplied by -3. I get 6, -6, 12, and 6. And all the numbers in row 2 get multiplied by 2. I get 6, 12, and 42. What do I do next? Now, what I do next is going to seem just a little weird because here I didn't write down equation 1. I just wrote down what I got when I added the equations, okay? So here's where something is a little different. I'm still going to write down row 1. But here I'm going to write down row 1 plus row 2. I'm going to ask if you would just do that for me. Write down what you get according to the instructions that I impose on this matrix. Okay. Now, first thing we do is we write down row 1, right? And row 1 hasn't changed. Okay, at least by this I mean row 1 from the last step. Okay. So row 1 is still going to be -6, 12, 6. Row 2 is going to become what we get when we add row 1 to row 2. Now, when we add the x or the y coefficients, we get -6 and 6, right? What's that up to? 0. So we put a 0 there. Okay. And then we add the 12 and the 12, and that goes here. And of course, that's 24. And then we add the 6 and the 42, that gives us 48. So it's clear how we do that? And here we do write down the zeros. Okay, over here we didn't have to because we're just going to solve the equation, and zeros just get in our way there. It wouldn't hurt anything, but it'd be extra stuff to worry about. Okay. Well, now I write down row 1, and I write down row 2 divided by 24. So we do it. Well, what we get is actually very simple. We write down equation 1 from the previous step. That's -6, 12, 6, and 0, 1, 2. Okay. Now, the other thing we don't have to do at this stage, we can complete the solution very easily. And I would normally do it in this step, but I want to separate the steps the first time we see this. We're going to divide row 1 by -6. And then we're going to write down row 2. All right. So if you divide equation 1 by -6, well, -6 divided by -6 is 1. 12 divided by -6 is -2. And 6 divided by -6 is -1. And then we have equation 2, which is still 0, 1, 2. Okay. Now let's see where we are. What we've done, well, let's see what we've done first. We've manipulated things to get a 1 here. Okay, that's one of our goals, to get a 0 here and a 1 here, because of what this equation tells us. We'll see in a minute what the equation tells us. And then we've done another step to get a 1 here. That's not going to necessarily give us a 0 here. It'll give us whatever we get here and whatever we get here, okay? So we can always do something like this. We can always get the equation down to 0, 1 down here and a 1 up here, okay? Let's go ahead and just interpret what these equations are. So tell me, what would the equation be for this if we were to write out the equation of the x's and the y's? Now, you probably don't leave yourself room to the left to do that, so you do it to the right. Doesn't matter. I could do it to the right. Matter of fact, maybe I will, because that's what most of you are going to have to do. Okay? I've got room to write this system out with x's and y's. And I've got room to write this system out with x's and y's. So we should do that for both this matrix and this matrix. Okay, now I do want to stress organization on the page. Okay, I said before that we want to keep the x's, y's, and z's all lined up here. And people have pretty much done that. I've seen a couple little glitches. And, you know, they just mentioned it. And I think people get the idea that we want these to stay lined up. Okay. And the one thing I ask you to do, everybody did this correctly, except not everybody put the equation for this one here and the equation for this one here. Okay. So we want to keep it lined up so we can see what the equations are. You notice that this equation corresponds to this matrix. This equation corresponds to this matrix, right? Now, we don't have room to write the equation that corresponds to this matrix, but you know what the equation was. Okay. But we can skip down to here and we can see that this corresponds to -6y plus 12z equals 6, and just 1z equals 2, which means that we've already, at this point, found the value of z. Okay. And of course, at this point, we could use back substitution. We could substitute that 2 in here and solve this equation for y. And sometimes that's what you want to do. Once you've found one of the variables, you go back, substitute, and get the other. Okay. And if you got 3 variables, well, we'll see whether we have time to work one out or not. We'll see the form of what you get and see how it works. Okay. Okay, well, that's what you get here. Down here, then you get plain old y minus 2z equals -1 and c equals 2. And at this stage, it's even easier to plug z in here because you won't have a coefficient in front of y. And just get y equals, comes right out. Okay. We're going to complete it. We're going to write it out so there's no question. So what I want you to do is I want you to do equation 1 plus row 1 plus 2 times row 2. And of course, we don't want to mess with row 2. Because row 2 already has a solution for z, right? So write out the matrix that you get if you do this. Okay, I'm seeing just a little bit of easily resolved confusion about this instruction, row 1 plus 2 times row 2. Okay, so let's first of all see how we can do that just looking at these numbers. This means we take every number in row 1 and add double the number in row 2, right? So if row 1 has a 1 in it, and row 2 has a 0, and we have the 1 plus 2 times 0, which is still 1. Okay. Now, if I've got a 0 here, it's not going to change this number. Okay. So we're going to have 1 here. Now, another thing that might be helpful is row 2 isn't going to change. So maybe the first thing we do is we write down row 2. Okay. Now, we have -2 in row 1. Okay. We have 1 in row 2. If we double what's in row 2, which is what this 2 times row 2 says, and add it to the number in row 1, what do we get? Well, we double the number in row 2 and add it to the number in row 1. If I double 1, I get 2. If I add that to -2, I get 0. So that's going to give me a 0 here, and that's why I did 2 times this row added to this row. I wanted to get a 0 here. You'll see why in a minute if you don't already. Well, then I do the same thing with these numbers. I take the number in row 2 and double it. That's going to double the 2. And I add that to the number in row 1. So I'm going to get double 2. That's going to be 4. Added to -1, which gives me 3. Okay. Now, what that gives me, if I write down the equation, well, write it down. Okay. Once you got this written down, write down the equation, the system of equations that you get from these numbers. Well, I don't have to explain this in detail to anybody here because everybody's got it, but just, for anybody who happens to be doing what they're supposed to be doing in the distance course, which is following this step by step and doing the same thing I asked the class to do. Okay. We interpret this equation as this is y, this is 0z, and this is 3 on the other side of the equal sign. So it's y plus 0z equals 3. But of course, 0z is just 0 no matter what z is. Okay, so I don't bother writing down the plus 0z. And this is 0y plus z equals 2. We don't write down the 0y, but I'm going to just emphasize, see what we could. But once we write down 0y, we realize that, well, that's 0 no matter what y is. So there's our system. And it's a good habit to keep y aligned, have a blank here. If you just write down y equals 3 here, it's okay, but you fail to respect the systematic representation of the system, okay? So I recommend you respect that all the way through the end, because it's going to be important when you get a system of 3 equations and 3 unknowns. Not that you couldn't adapt, but why adapt when you don't have to, okay? Well, that's the solution. And of course, up here, if we substitute the z equals 2 back into one of the equations, we're going to get y equals 3, okay? So we haven't completed this solution, but I think everybody knows how to complete it. This is how you complete it with the augmented matrix. Now you need to know this because once you learn how to do this and know what it means, and know that you can do it yourself, it's very easy to go to Wolfram Alpha or Desmos or anything online and type in the augmented matrix and ask it to row reduce that matrix. And it'll just take this matrix and spit this one out. And knowing what this means is here's your solution. Okay? Now, don't do your homework that way because you're going to have to show me all these steps correctly on the exam. Okay? And please make sure you learn to do this in a way that you're going to retain for at least 2.5 weeks. Okay? so you don't screw this up on the exam, because this little practice is really easy. But it takes some practice, and you have to make sure you understand how to write out these instructions and complete them. Now, I don't think open math necessarily writes instructions out in the same compact way I do here. I'm not even sure that all videos you would be able to see even bother to write it out. Okay? Pedagogically, I have to assume that they've got an equally good alternative. Okay? Maybe even a better one. And no, you can also check these out on Khan Academy. They're great. In many cases, I think they're better than open math. Okay? So you go look up the topic, augmented matrices, Khan Academy, give you the whole thing. And he's very good. Okay. Or you can look at my video, which you've already been through and probably already know. So maybe it's better that you look at somebody else's stuff. Okay. Because everybody followed all these instructions, just little glitches here. I think you understand how to get it. This is the row echelon form. Okay. The row echelon form translates directly into the solution. Now, if you look at what we've done with the matrices, we've done whatever's necessary to get the zero that we want here. Okay, that corresponds to eliminating y. So we've got a zero here. Okay. And then once we get a zero here, it's really easy to get a one here. We just divide by 24. The whole row. All these operations work on the entire row. And there's our z. Okay. And again, this is what we call upper triangular form. Okay. You know, the numbers here form a triangle. And it's an upper triangle because it's wider here than it is here. Make sense? So this is upper triangular form. Okay. It's also upper triangular with a 1 here, which is handy. Because now you got to do substitute 2 for z and you can solve for 1. Okay. This is a reduced upper triangular form. Okay. I think I'm using these words right. So when I took my first linear algebra course, I never did understand what these words meant. Partly because the instructor had a very strong accent. Like when he talked about the degree of a polynomial, he didn't say degree, he said diggity. There's a fairly recent popular song, less than a decade earlier. It went hot diggity, dog diggity, boom, what you do to me. Okay? And it was a song, and it's kind of in the mid to late 50s. It was kind of a neat song. So I kept thinking he was talking about that song. What's this have to do with linear algebra? Okay. And it was a very tough linear algebra course at a very tough school of technology. So I learned to do all this, but I never understood what these words meant. It was never explained, and I just couldn't quite pull those words out of the book the way it was done. Okay. And it's my fault for not being a particularly great reader. Hold on, see if I'm adequate. But if I'd have there have been such things as videos back in those days. I mean, we were just a decade away from carving images into the walls of our caves. And there was no such thing. There was no access to these kinds of explanations. It would have saved me a lot of trouble and maybe we had made an A in that course instead of a B. Okay. Now, B was a really good grade back in those days. A was just a few people got A's. Okay. It would save me enough time and enough agony in trying to figure out what the words meant. Okay. My point is, we'll make use of the materials that are out there, right? Make use of the videos, but and make sure I've got the words right. They're going to tell you. Everybody's going to tell you. Okay. This is the ultimate reduced form. Okay. So I'm going to use the word ultimate here. This is where we end up if we want the whole thing to be done with these matrices. So we just have to read off the solution. Okay. Now, if you tell Wolfram alpha to row reduced, that's what it's going to give you. You don't have to tell row reduced to the, reduced echelon form. And, I use the words upper triangular here because I had them before. But it's just reduced echelon. You don't need the upper triangular. That's implicit. All right. Well, I think we're having a significant amount of fun already. Think you're going to be able to follow that process? Sometimes things go haywire. Like when you do this step, if I had a 12 here and a negative 12 here, I get 0, 0, 48, wouldn't I? What would that tell me? It tells me ain't no solution because 0 can't equal 48. And it tells me that 0 equals 48. Okay? So if there's a solution, then 0 equals 48. So there's no solution. That would correspond to the lines that represent these equations on an XY coordinate system being parallel. Okay? I think you're going to see that. If it said 0, 0, 0, then that's no contradiction. But that would mean that you have infinitely many solutions. Any solution that satisfies this equation would work. So Z could be anything at all. You would get a Y. Y could be anything at all. You would get a Z. So I'm not going to test you on that, but it's really good to understand that going forward, especially if you have a linear algebra course in the future. Okay? There's only so much we can do here. And again, it's done really smoothly with this group, which is unusual. Make sure you've got the process down because we do it with 3 equations and 3 unknowns. Okay. Well, if you have 3 equations and 3 unknowns, I'm going to show you the form of what you get because you got to see examples. Food problems. And then if we have time, I'll try to make up a problem that really does have a solution. Okay. So far, I've been at 100% on that dude in my head. But eventually it's going to go all to heck and I'm going to give you something ugly. Okay. Of course, in the real world, everything's ugly when you come to the mathematics. Okay. The real world is very uncooperative at giving you nice integer solutions. All right. I'm reading this thing on general relativity. And the guy who's a top line research, he's 10 years older than I am, but he's doing this series. He's still doing really well. Okay. 10 years from now, I'm not sure I'll be able to say really well. He has one of the top people in the world. And he says, in one place, he says, well, general relativity has a reputation for being hard. That's Einstein's theory of general relativity. Okay. He says, well, that's because it's really hard. Okay, but the ideas are simple. I mean, they're simple if you have a undergraduate degree in mathematics and physics. Okay. Even an undergraduate degree, a good undergraduate degree, some of them aren't so good, much less graduate work. So, I can understand what he means. Most people are not going to understand it, but there are enough people. It's in the Stanford area, and he had a class full of people that he went through the whole thing with. Okay. And he said, we're not going to do those hard calculations just because they're really messy. You sit down with a sheet of paper and you do calculations, and you have 100 sheets of paper at the end of the afternoon. He does his calculations faster than I think I will. But yeah, guy's a certified genius. Well, the point is, by analogy here, this is general relativity. It's way, 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 way far from general relativity. It's an undergraduate degree in mathematics and physics away from understanding a little bit about general relativity. Okay. You can understand how this might work. Okay. So basically, we have a 3x3 matrix. Okay. So let's just put some numbers up here. 3, 5, 7, -4, 6, -9, 3.93. Okay. 5.01 to -5. Whatever these numbers are, okay, we're not going to do these numbers. So I can write anything I want up there. I can make it even worse. Maybe this is a square root of 5. Okay. Whatever the numbers are, you can at least approximately reduce this thing if the equations, if you have a closed form solution for all three variables, like this is x, this is y, this is c, this is to the right of the equal sign. Okay. You would reduce this to 1, 0, 0. And an asterisk like this stands for just some number that comes out of the process. Okay. And I'll just put 2 asterisks for this number, 3 asterisks for this number. So maybe the asterisks stand for, these stand for 3 different numbers. We don't want to confuse it with an asterisk, just a single asterisk, saying they could all be different numbers. It's less confusing if we do this. Okay, well, write down the equation for this one. Write down the system of equations for this. And write down the system of equations for this. Okay, everybody's got it. I mean, I didn't check every last detail, but I saw 3 equations, x's, y's, and z's, and I saw most of these numbers. So I'm pretty sure everybody got it. This equation would be 3x plus the square root of 5y plus 7z equals 2. This would be -4x plus 6y minus 9z equals 3.93. This would be 5.01x plus 2y minus 5z equals 12. Now, one thing to notice in this equation, just for general purposes, square root of 5 is not something you can write down exactly with numbers, with the decimal numbers, okay? And pi is not something you can write down exactly with decimal numbers. So you'd have to make a decision how far to round off here and how far to round off there. And that's a subtle thing that you talk about in numerical linear algebra. Okay, nothing that we need to talk about here. My bottom line is I'd never ask you to solve that. Okay, I'll probably give you something that just comes out in integers, or maybe there's one fraction or something. Okay, I don't want to strain you on this just introduction to matrices and how they can work with systems of equations. Okay, so anyhow, this one gives you z equals asterisk, y equals, well, it's a double asterisk, and z equals triple asterisk. Okay, now how do you get from here? This up, this. Disaster. Okay, so here we have what a system might look like. I don't want to do this with the numbers. I just don't have time to work through all the numbers. You'll probably see one with 3 equations, and you'll see a video that shows you how to proceed. I'm just going to show you how the form of the matrix evolves. Okay, so we start with a matrix. Now, every one of these asterisks stands for some number. They don't all stand for the same number. If they did, it'd be a pretty trivial system. Okay, but you start out with a bunch of asterisks. All right, and then what you want is you want to get 1 here. Okay. Once you have a 1 here, it's really easy to see what multiple of the first row you add to the second row to get a 0 here, and what multiple of the first row you add to the third row to get a 0 here. Okay? Because the next thing you're going to want is you want to get the form to go to this. Okay? You want to get 2 zeros here. Now let me just ask you. You know this number. What operation do you do in order to get a 1 here? That number was 3, let's say. Wouldn't you just divide the first row by 3? Sure. Is that difficult to understand? Well, that's really easy to understand. Everybody has light in their eyes. It shows me they understand that completely. Okay? It's really easy to get a 1 here. Assuming you don't have a 0 here or something. Now, there's another thing you can do that you don't have. I'm not going to have you do that in this course. You could switch rows. It doesn't matter which order the 3 equations are written down. It's still the same 3 equations, right? So if you happen to have a 0 here, pick one of the other rows that doesn't have a 0 and switch those 2 rows. Okay? So you get a 1 here. The only way then you wouldn't be able to get a 1 here if you didn't have a 1 for any of these, which would be something completely different. We're not going to talk about. Okay? Take a linear algebra course is one of the first things you talk about. Now, we want to get zeros here. So it's easy to understand how you get zeros here. Like 5 in front of it. 5 is my coefficient here. I'd subtract 5 times the first row, right? If I had a -7 here, I'd add 7 times the first row to get 0 here, right? You've already done stuff like that. So it's real easy to get this point. Okay, then, I'm sure we see where we're going. If I've got this, and if this isn't 0, then I can easily get a 1 here, can't I? Just divide by whatever this number is, over, and I get a 1. Okay? If I have a 0 here, but don't have a 0 here, at that point, I can switch these 2 rows. I can switch rows anytime I want to. Still the same 3 equations. Okay? Still equivalent to the first system, still has the same solutions as the first original system. Every step here consists of equations that have the same solution. So that when you get down to the last step, it looks like this. The solution is right there in front of you, and it's a solution to every equation, every system that you have in the process. Okay, so click on this number here. It's not 0, divide by it, and you get a 1. Divide the whole row. You got to do what you do to the whole row. Okay? Then you're going to get a 1. Then, now that you got a 1 here, it's really easy. You get a 0 here, isn't it? Whatever number's here, I add minus that number times this row to this row, and I get a 0. And I'm going to have 0, 1, asterisk, asterisk. And I'm going to have 0, 0, asterisk, asterisk. Okay? Because anytime I've got a 1 in a column, I can wipe out everything else in that column. Okay? Well, now the last thing, well, 2 more things I got to do. What do you think I'm going to do next? I'm going to give you a chance to tell me what you think I want in the next step. Okay, so I'm going to pretty much told you. 1 here. Well, that's the pattern. That's what we want. Okay, so that's very good. You're understanding. We want to get 1, 0, asterisk, asterisk, 0, 1, asterisk, asterisk. We're not going to mess with these 2 rows. We're going to pick on this row and get 0, 0, 1. And of course, to do that, whatever this number is, we divide this row by that number. And we get an asterisk. Okay? Okay. Now, see if you tell me what to do next. Okay, so I got a really good answer. So we want zeros above the 1. Because if we've got them, then we got this one. Okay. And it's really easy to do that. You got a 1 here. It's easy to wipe out this number and this number. Okay. That's all there is to it. You just got to do the calculations. Now, the analogy I gave you before, general relativity is really hard, but mainly because the calculations are really a pain. There's some serious conceptual things that I'm still struggling with. Okay. But you know, everything fits into mathematics, and I know this is a matter. I'm trying to do this without writing it down. And I've said that before, I think. You don't learn mathematics by doing it in your head and not writing it down. Okay. Yeah, I got this problem, which came just recently after I've been not writing things down for a long time. I'm trying to see how much I can get in my head without writing it down. And I'm never going to research relativity. Okay. Okay. So analogous to what this guy said, well, general relativity is really hard, but it's because of the details, not because of the general ideas. The only difficulty in this is getting the steps right. You see where you go. If I gave you one that had 4 rows with 4 asterisks and then another, so there are 5 asterisks in each row, you'd be able to tell me what the process is. You get a 1 here, you wipe out everything below it. Then you get a 1 here, and wipe out everything above and below it. Then you get a 1 here, wipe out everything above and below it. And if there is another row, you get a 1 there and wipe out everything above and below it. The conceptual difficulty comes not in this course, later on, when you have to interpret what happens if you get too many zeros. Okay. And we're not going to, again, that goes beyond what we're trying to do is just give you enough matrix stuff that you can function with matrices, which don't just occur in linear algebra, they occur in business courses. Okay. At a lower level, usually the linear algebra, unless you're going into deep finance, okay, which takes a bit of mathematical genius to be good at, okay. So that's about as far as we've gone, except for one more thing, which is also pretty easy. So I want to go back. I can find that first set of equations. And just show you everybody okay here? I'm going to cover it up. Show you this system here. Because one thing you learned was how to multiply matrices, right? Rows times columns and all that stuff. Okay. So let's just see. Okay. We're not going to mess with this side. We're just going to do this matrix multiplication here. Row times column, row times column. Okay. Apparently we didn't do row times column in here. I spent a lot of time doing it in the MDE class. Okay. Let's see how that's done. You can, of course, look at that class, but you probably have other things to do. So I'm not going to put that on the test. Okay. So I just spent a couple minutes with half here, showing you how this works. It's as simple as everything else we've done, maybe even simpler. Okay. This row times this column is 5 times 2 plus 3 times -4. We just match up the first number of the row with the first number of the column and multiply it, right? So that's 5 times 2. And then the second number in the row by the second number in the column. Okay. And if we do this, we get 10 minus 12. That comes down to -2. Okay. Now, in this calculation here, first of all, right off to the side, what do you get if you do 2 -4 multiplied by y6? Just write it out. Okay, again, the rule for a row times a column is always the same. Take the first number of the row multiplied by the first number of the column. Add that to the second number in the row times the second number in the column. Then if you have another number in the row and another number in the column, do the same thing to those. And continue until you get to the end. Unless you have more numbers in the row than you have in the column, in which case you can't do it. You just say you can't do the multiplication. You don't have enough numbers in either the row or the column to match up with the others. Okay, you got to be able to match them all up. Does that make sense? And I think you are going to see that in the whole. Okay, so if you do, then it will be on the exam, but it's easier than what we did there. Okay, so you multiply this out, that equals 2y minus 4z. Okay, so you put 2y minus 4z. Since it came from the first row, you put it in the first row. Now you're going to do the second row, and you're going to put the result in the second row. So what are you going to get? Okay. We get 3 times y and 6 times 6. So it's 3y plus 6z, right? Everybody understand? Now, this tells you if the numbers here are equal to the numbers here, then 2y minus 4z has to be equal to 2, right? And 3y plus 6z has to be equal to 1. Okay? Well, where did I get this matrix? Uh-oh. This is not supposed to be 1. This is supposed to be 21. That's really easy to change that. Okay. Because what we have here is just the system that we started class with. Okay. Now there's another way to solve the system. It's to solve this equation. Okay. This is something else that you can easily do with a number of different bits of software. So okay, I should have some more space. Got some more space. Yeah. To get the solution of this system, then you write the system as a matrix equation: 2, -4, 3, 6 times, it's y and z in this case. I think I might use x and y. I think I use this equals 221. Okay. I multiply both sides of this equation by the inverse of this matrix. Okay. Now, just like if you compose F with F inverse, so F of F inverse of X is just X. That's the way you test inverses. Remember, you're going to be able to need to do that on the exam. We'll do some review because that's all about that. Okay. The inverse times this just leaves us with YZ times 221. I don't expect you to be able to go home and do this, but maybe. I mean, if you pursue it, especially if you've got an engineering curriculum or something like that in your future, a future with a lot of mathematics, be worth your time, but you try to prepare for finals, so probably not going to want to spend the time. That's fine. Okay. To get the inverse, you write down 2 negative 4, 3, 6. And augment that with 1, 0, 0, 1. And you're kind of familiar with that because it's what you want to end up with when you do the augmented matrix. And you reduce this to where you have 1, 0, 0, 1 here. And when you do those operations, they're going to apply to the whole row, whatever operations you happen to do. And these numbers here, the 1, 0, and 0, 1, are going to change to something else. You're going to get a 1 here, right? So you're going to divide this row by 2, so you're going to have a 1/2 here, right? Then you're going to add a multiple. You're going to add negative 3 times this row to this one, which will give you negative 3/2 here and a 1 here. And then you're going to do other things that are going to change the zeros to something else. Okay? This part of the matrix here is your inverse. You could easily do this. If we had another half a class to spend, I could show you completely how to do this, but we're not going to do that. It's a little more than is appropriate, okay? But that's kind of where it heads. So get good at doing the augmented matrices, and you should be pretty good at everything else. And at some point, the blank camera started giving us a blurry focus. So I will just get that in focus. And I'll put up a series of bullets there just in case people need to see them. I think it could still be read, but it's aggravating as heck. Okay, at some point the camera went blurry. So I'm just going to kind of recapitulate what we did without going through all the details. We started by solving this problem, this system of equations by elimination. And that was fairly straightforward. Everybody did that with no problem. Then we wrote down the coefficients and the numbers in this system as an augmented matrix. 2, negative 4, and the negative 2 went in the first row. The 3, the 6, and the 21 went in the second row. Then we added multiples of rows, multiplied rows by things, and so forth. Multiplied the first row by negative 3, the second row by 2. Get this system. Then we added, we wrote down the first row, added row 1 and row 2, and we got this system. And then we divided row 2 here by 24. Got 1, 2, which corresponded to z equals 2. So this system here corresponds to this system, which could easily be solved on its own. Just back substitute that z equals 2 here, and you get a solution. Okay. Then we moved on to get what we call the reduced echelon form, row reduced echelon form of the matrix. 2 more steps. There's an advantage to doing this. We divided the first row here by 6, negative 6. First row divided by negative 6 gives us this. So now we have a system similar to this one, even easier to solve if we plug in z equals 2, because we've already got y sitting here. We just add whatever that number is to both sides. We've got it. Then we add row 1 to 2 times row 2. Why? When we do that, this negative 2 will become a 0. This negative 1 will become a 3. And we went over some detail there. And this corresponds to this system. There's our solution. That's a solution to the system. We can plug it in. We could have solved here, but back substitute z equals 2 in the other equation. We would have gotten the same thing. And everybody was right on top of this. It's very good. Okay. Now, let's see where I was next. Okay, again. Looking at how this system evolved, the first thing that we did was we could do is get a 1 here, so we get a 0 here. Okay, and then we can easily get a 1 here, and so forth. Okay, well, let's see how that works if we've got a 3 by 3 matrix. Ultimately, what we want is a solution to the system, which looks like this. We've got 1 here, we got a 1 here, we got a 1 here, everything else is a 0. If this is a system in x, y, and z, then we have x equals whatever this number is, y equals whatever this number is, z equals whatever this number is. Well, if our system starts here, the first thing we will generally want to do is get a 1 here. That's easy to do. Whatever this number is, we just divide this row by that number, and we get a row that has 1 in front of it. Then, once we have a 1 here, we add this row. Well, we take whatever this number is, we multiply this row by the negative of that number, so that when we add the result to this one, we get a 0. And we do the same here. So having a 1 here makes it really easy to get zeros here. Okay. So we're on our way. We've already got our first column, 1, 0, 0. Now, next thing we want is to get the second column to look like this. First thing we're going to need is a 1 here. Well, take whatever this number is, divide it into all the numbers in this row, we'll get a 1. Having a 1 here, we just multiply these by the appropriate numbers. We'll get zeros here and here. Okay? And then the obvious thing, and everybody in class is able to tell me quickly what it was, which we can get a 1 here, which will make it easy to get zeros here. That's the process when you have a 3 by 3 system. This is how 3 by 3 system evolves. So the devil's in the details. You want to be very careful that you do the arithmetic correctly. But other than that, it's quite easy to solve the system with just a little practice. Now, there's another thing we can do. Here's a matrix product. Okay? I multiply this matrix by the YZ column to get this column. Okay, well, how do you do that? You have to know how to multiply a row by a column. Well, down here, let's just take, these numbers aren't relevant to this system. But let's just say we got 5, 3 in a row, 2, negative 4 in a column. You can multiply a row by a column. All you do is you take the first number in the row times the first number in the column. In this case, that would be 5 times 2. So we've got it. You take the second number in the row and the second number in the column, and you multiply those together, and you add the results. So it's just this times this, first row, first number times first number, and then the second number times second number. And if you got a third number here and a third number here, you do third number times a third number. If the length of the row doesn't match the length of the column, so you don't have a number to match up here with every number here, then you can't do the multiplication and the row cannot multiply the column. So it will be undefined. Anyhow, doing this, very simple. We get this and this, add it up, we get negative 2. Now, here we have a row and a column. Multiply this row by this column. Well, that corresponds to 2 times negative 4 times the y z. We get 2y minus 1. 2 times the first number. First number times first number gives us 2y. Second number times second number gives us negative 4z. And we write that down here. Okay. And then we do the second row times this column, and we're going to write the result in the second row of this matrix. Okay. Well, we didn't write it out. It's 3 times y. There it is. It's 6 times z. There it is. And that equals 221. That matches up here to give us, well, that matches up. If this is going to equal this, now the number here has to equal the number here. So 2y minus 4z has to be equal to 2. So we write that down. And then 3y plus 6z is going to have to equal 21 because the second number here has to be the second number here. There it is. Now, where did that come from? Well, it came from this system of equations that we solved really at the beginning of class, actually. All right. 2y minus 4z equals 2 right here. 3y plus 6z equals 21 right here. If we're looking at this system, we understand now, at least if we process everything that we've done, that this system can be written as this matrix multiplication, because that's what we just looked at. Okay, if I do this multiplication, I end up with this system. So this system is equivalent to this, and it's easy to see how to set up the matrix. We just take the 4 numbers we're going to have here, take our YZ, put them here, take the negative 221, put them here, and we've got it. Now, what I said was, and this goes a little beyond what we can do, but it's worth thinking about. If we multiply both sides of this system, or both sides of this equation by the inverse of this matrix, whatever that means. Now, just like f inverse of f of x equals x, something you need to be familiar with if you've forgotten it, because you have a final exam coming up in 2 weeks. Okay? The inverse undoes what the function did in the first place. So f inverse of f of x just gives you x. Well, the inverse matrix times this matrix just gives you yz. Totally analogous to the way inverse functions work. And if that doesn't click, and it might well not at this point of the semester, just understand that the inverse times this leads us to whatever this is. Now we do the inverse times this matrix because we do to both sides. Multiply both sides by the inverse matrix. It looks like this. Now, how do we get the inverse matrix? You just don't use 1/2 and negative 1/4 and 1/3 and 1/6 or something like that. It's not obvious. What you do is you do an augmented matrix here. You put the 2, negative 4, 3, 6 matrix here, and you put 1, 0, 0, 1, which you should be familiar with if you've been through the rest of the class today. Okay? That's called the identity matrix. You haven't used that terminology. You put that matrix in. Okay? And then you row reduce this thing. So you row reduce. In other words, using the process and develop, okay? And these numbers are going to get operated on. Like when you do 1/2 of the first row to get a 1 here, you're going to have a 1/2 here then, okay? And then when you add -3 times the first row, where you got the 1 here, to the second row to get a 0, that's going to give you -3/2 here. 0 is going to become a -3/2. And then you have a couple more operations to do, which will change this 0 and this 1 into other numbers. Whatever numbers those get changed into, that's your inverse matrix. So you just put those numbers here, okay? And you get, and I'll write it out here. I can find white chalk, I can write it out with white chalk. Didn't use it white chalk. Okay, you get YZ equals, well, whatever those 4 numbers are here, times 221. So these numbers go here. Now, you'll have numbers, so you can multiply this out, and you get Y, and you get Z. Very simple and very elegant and very neat. I did comment, and hopefully heard those comments, but I did comment that I'm not going to ask you to find inverse matrices. I might put it on there as an extra credit to see if some of you really pretty good at this. Any of you are, most of you are. So with a little instruction, I might even give you the opportunity to show off and do that. And if it succeeds, I'll average your score and that problem in. If it doesn't help you, great. I'll just, thanks for trying. Okay. But it's not going to hurt you, great. All right. Well, there we have it. Now, I did that just so, I don't know when the camera blurred, but that covers most of what we saw in class. There's a little bit that I didn't include here, but I'm not going to include that. Because when the camera blurred, it didn't blur that badly. You should still be able to read what was there. It's just a little bit aggravating.